Dear learners, welcome to the session on inferential statistics. In this session, we are going to learn something about inferential statistics. You know the advantages of statistics in social science research, how effectively we can present the data, how effectively we can make the analysis with the help of statistical data. You also exposed to descriptive statistics, where we have discussed about various statistical measures to describe the data, like descriptives, mean, median, mode, measures of variation, and so on and so forth. The concept of descriptive statistics is to describe the data with the help of measures of central tendency and measures of dispersion. The concept of inferential statistics deals with the generalizing the samples to the population. When we have the universe or population, we may not study the entire population or entire universe. Then we take a sample and we study the sample, and once we study the sample, we are trying to generalize the findings of sample to the population. We try to estimate the population parameter by using sample, and also in inferential statistics we do hypothesis testing and trying to know the relationships among variables like dependency, independent, and the cause and effect relationship, and the contribution of the variable, independent variable to the dependent variable, how and when, what is the proportion of these independent variables, whether they are contributing for dependent variable or not. Then there is a direct effect or indirect effect, and also trying to know the relationships, associations. Also we see the inferential statistics helps the researcher to do the research on the sample and extrapolate the findings of the sample to the population. It uses a sample data to evaluate the credibility of a hypothesis about a population. So when we have the research, there is a research problem. We are intended to study the entire population. Due to the resource constraint, we go for the sample, and you must have learnt various tools and techniques of sampling, and there are various issues in identification of the sample, a right sample. Once you are sure that your sample is a representative sample, your sample is unbiased sample, your sample size is sufficient enough, then we conduct some survey on the sample. If it is a survey research, we conduct survey on the sample, and if it is a experimental research, we conduct experiments on the sample. Once we have the sample results, then we are trying to extrapolate these sample results to the population. Then we may estimate the population parameter, or we may also draw some kind of inferences about the population by using the sample. So in a nutshell, the inferential statistics helps the researcher to have the overall idea about the population without studying the population, whereas he or she studies only sample. Before we proceed further, I would like to introduce some of the technical terms what mostly used in inferential statistics. The most popular word or words which we can use, one is statistic, second one is parameter. The statistic is descriptive of a sample. As all of you know, the descriptive means the measure which describe the group, like the measures of central tendency, measures of variation, or measures of dispersion are popularly known as descriptives. The descriptive of a sample is known as statistic. For example, mean of the sample, median of the sample, mode of the sample, standard deviation of the sample, and so on. Whereas the parameter is descriptive of a population. Again, here the parameter is the mean of the population, standard deviation of the population. Here the challenge is, given the sample mean, how do I estimate population mean? That is where is the challenge is. So, the inferential statistics is again studying the parameter which through the statistic. Whenever I say parameter, it is associated with the population. Whenever I say statistic, it is associated with sample. The next important word is sampling error. The sampling error, whereas it explains the variability between the sample mean and population mean. When I am trying to estimate the population mean, there is a population, that population will have some mean, but I do not know the mean of the population, but I am trying to estimate the mean of the population, for which we take the sample, calculate the sample mean, and if the difference between the population mean, actual population mean and the sample mean is nothing but sampling error. The sampling error may be less, sampling error may be more, it all depends on various issues of your sample size, representativeness of the sample, and how far your sample is going to explain the parameters of the characteristics of population. The next important word is confidence interval. A confidence interval gives an estimated range of values which is likely to include an unknown population parameter, the estimated range being calculated from a given set of sample data. Say for example, there is a population, from that population we have chosen a sample of 100 items. For 100 items we have a sample mean of 50. Now I would like to know what is the population mean. If I look at the population mean of mu, that is usually population mean is denoted by mu and the sample mean is denoted by x bar. We are interested to know the mu given the x bar. So one kind of option is mu is equal to x bar, the another kind of a option is mu is equal to x bar plus or minus some value. That x bar plus or minus some value, now when I say, that is nothing but confidence interval. So here we are trying to estimate the range of values which is likely to include an unknown population parameter, the estimated range being calculated from a given set of sample data. The next to confidence interval, I would like to introduce you standard error. In standard error, it is the standard deviation of the sampling distribution of a sample mean. So I would like to give you an example. There is a university. The university has about 5,000 students. I would like to draw a sample of 100. So if I draw one sample of 100, I get one sample mean. If I get another sample of another 100, I get another sample mean. If I take another sample of 100, I get another sample mean. So one is x1 bar, second one is x2 bar, third one is x3 bar, fourth one is x4 bar, and so on and so forth. When we have so many sample means, but all sample means are not equal. But if I would like to calculate the standard deviation of sample means from their grand mean, the grand mean is nothing but mean of the means. If I have several means, I would like to have mean of the means. Once I have mean of the means, I would like to find out the standard deviation from mean of the means to means, sample means. So that is known as standard error. The standard error is nothing but it is standard deviation of the sampling distribution of a sample mean. The next important term is confidence interval. This confidence interval is equal to observed mean plus or minus z, that alpha by 2, alpha is known as level of significance, multiplied by sigma by square root of n. Here the confidence interval means when I have a sample mean, I would like to know where my sample population mean lies, for which I am going to give an interval that is called interval estimate. The interval estimate is calculated by using the observed mean plus or minus z alpha by 2 star sigma by square root of n. Whereas here observed mean is sample mean, then sigma is standard deviation of the population and n is the sample size. Sigma by square root of n is known as standard error. In the earlier slide, we are trying to understand the standard error. The standard error is nothing but standard deviations of the sample mean. So, that can be theoretically approximated as sigma by square root of n, where sigma is the population standard deviation. By any chance, population standard deviation sigma is not available, we try to replace it with S, that is sample standard deviation. So, in the absence of population standard deviation sigma, we can also use S, that is sample standard deviation, by square root of n. N is nothing but sample size. Then the next question is what is Z, and also we have alpha. The alpha is nothing but level of significance. Level of significance, usually this level of significance is 1%, 5% and 10%. 1% level of significance, 5% level of significance and 10% level of significance. The 1% level of significance will give you 99% confidence, 5% level of significance will give you 95% confidence level, 10% of level of significance will give you 90%. So, how I am arriving confidence level from the level of significance? 100 minus level of significance is confidence level. The alpha is popularly known as level of significance. Why it is by 2? That is the next question. Say for example, I have alpha value as 5, then 5 by 2, 2.5%. So, 2.5% one side, 2.5% another side. So, for example, my level of confidence is 95% or level of significance is 5%. Say for example, if I make an estimation of the population mean 100 times, I may have 100 intervals, then 95 intervals are going to contain the population mean. In 5 of the intervals, the population mean may not contain. So, out of 5 also, 2.5 times the population mean is above the interval, 2.5% of the times the population mean is below the interval. Then Z is the corresponding value. Given the alpha from normal distribution, we are trying to have the Z values. The popular Z values are 1.65, 1.96, 2.58 and so on. Once you look at the normal distribution, that normal distribution will have the standardized Z values given level of significance. So, that means the confidence interval will be calculated based on observed mean plus Z into alpha by Z alpha 2 into sigma by square root of n. The sigma by is the standard deviation of the population, sigma by square root of n is the standard error. So, by using this I am trying to get the confidence interval. Then the next important issue in inferential statistics is hypothesis, because we have started our discussion on inferential statistics with hypothesis. In hypothesis, we would like to understand what do you mean by hypothesis. So, if you look at the meaning of hypothesis in a dictionary, it says an idea or explanation for something that is based on known facts but not yet been proved. So, an idea or explanation for something that is based on known facts but not yet been proved. So, in the research also, the researcher may have some idea and the researcher may have some explanation for some study field, study area, but that is based on known facts but not yet been proved. So, what do you mean by this known facts? Sometimes these known facts are the literature support, the literature review. The literature review, the earlier researchers must have said something about it, that becomes a known fact, or the researcher himself or herself has an experience, but when we are trying to generalize the personal experiences or theoretical findings, we would like to frame a kind of a hypothesis. So, that means it is based on known facts but not yet been proved. The next kind of a definition is a proposition or set of propositions, because sometimes we have hypothesis, sometimes we have plural of hypothesis is hypothesis. That means in the thesis you may have the research thesis and research project, you may have multiple hypotheses. They set forth as an explanation for the occurrence of some specified group of phenomena. If you look at our social science research, we are trying to understand the phenomena, we are trying to understand some trend, we are trying to understand the cause and effect relationship we are trying to understand the association, we are trying to understand the relationship. So it set forth as an explanation for the occurrence of some specified group of phenomena, either asserted merely as a provisional conjecture to guide investigation. That is what is called working hypothesis. As a researcher, sometimes we may make working hypothesis only to move further. For example, I would like to know which gender is a quick learner. For example, most of us are teachers. When we teach, we would like to know which gender the students belong to, which gender are learning fast. So there, for a working hypothesis, we would like to say there is a difference between both the genders, or one gender is better than other. Sometimes this kind of a hypothesis is framed based on the literature, or sometimes it would be used as a working hypothesis to guide our investigation, and sometimes it is also accepted as highly probable in the light of established facts. That means whenever you frame a hypothesis, formulate a hypothesis, we need to test the hypothesis, so that can be accepted as highly probable in the light of established facts. So when I say hypothesis, this hypothesis is divided again into two kinds of hypothesis. One is null hypothesis, second one is alternative hypothesis. This alternative hypothesis also can be called as a research hypothesis. Here the statement being tested in a test of statistical significance is called null hypothesis. The test of significance is designed to assess the strength of the evidence against the null hypothesis. Usually the null hypothesis is a statement of no effect or no difference. Again, I am going back to the earlier example. I would like to study the difference between both the genders as far as learning is concerned. The null hypothesis says there is no difference between both the genders as far as learning is concerned. So in this context, what we are trying to understand is there is no difference between both the genders. Sometimes I can take one more example where I would like to give a kind of a medicine or pesticide, a medicine for a human being or pesticide for a crop. Then I would like to see whether is there any effect of this particular medicine or drug on somebody, for which the null hypothesis says there is no effect, So that means always a null hypothesis is a statement of no effect or no difference. Sometimes I am trying to compare the wages of two sectors, one is organized sector and another one is unorganized sector. So I would like to know whether the difference between both the sectors is 0 or not. That means both the wage structure in both the sectors is same or not, for which the null hypothesis says there is no difference between both the sectors. So, but this is also tested in a test of statistical significance. The statement is being tested in a test of statistical significance. So, the test of significance is designed to assess the strength of the evidence against the null hypothesis. So, whenever you have a null hypothesis, as a researcher, if you wanted to prove or disprove the null hypothesis, you need to get the data. Sometimes it is pro to null hypothesis, it is against to null hypothesis. So, if the data whatever we have established, if it fails to reject null hypothesis, then null hypothesis is true. Sometimes it is fails to prove null hypothesis, then or it fails to prove the null hypothesis, when I can say it is the null hypothesis is true, otherwise null hypothesis is false. So that means when we are speaking about null hypothesis, we are trying to understand the assumption whatever we made between two groups, or sometimes it is also between a sample and population. It need not be always between two groups. Even for one population also, I have some sample data, I would like to see whether sample mean equals to population mean or not. But ultimately the null hypothesis speaks about no effect or no difference. The second hypothesis is either research hypothesis or alternative hypothesis, alternate hypothesis. The research hypothesis is the hypothesis the researcher attempts to demonstrate to be true. Since this is the hypothesis deemed to be the most important to the researcher, it will not be declared true unless the sample data strongly indicates that it is true. That means as a researcher, one would like to test the hypothesis. Say for example, the intervention by the government to eradicate poverty, to minimize illiteracy. So then there are several measures are taken by the government, various governments. As a researcher would like to either prove or disprove the intervention has positively influenced the effect. So that means the wherever is the cause, then there is an effect. So we are trying to see the cause and effect, the kind of a relationship we are trying to look at. So as a researcher, I am trying to look at the intervention is positively contributed, not at all contributed, or negatively contributed. This is how the researcher would like to prove, for which the researcher attempts to demonstrate it is to be true. Since this is the hypothesis deemed to be the most important to the researcher, it will not be declared true unless the sample data strongly indicates that it is true. That means now once you make a null hypothesis followed by alternate hypothesis, then we have a sample, then we study the sample, from the sample we are getting the evidence. This evidence becomes very crucial to reject or do not reject the null hypothesis. Let us look at the steps involved in hypothesis testing. One is formulate the hypothesis. That means, as we have discussed now, null hypothesis and alternate hypothesis. Then the select appropriate test. So when I say select appropriate test, tests are broadly classified into parametric test and non-parametric test. And in parametric test, we make an assumption of normality of the population. That means if I am drawing a sample from the population, I assume that the population from which the sample is coming, that population approximates to normal. That kind of tests, with that assumption whatever we do, are called parametric test. The example for parametric test is Z-test, T-test, F-test, ANOVA, analysis of variance. Whereas the non-parametric test, we are not going to make any assumption about the population distribution. That is why they are called distribution free tests. Then there we are not making any assumption of normality. Then the chi-square test is one of the popular non-parametric tests, followed by some other tests like Kolmogorov-Smirnov test, Wilcoxon matched pair test, Mann-Whitney U-test, and so on and so forth. So that means based on the data, based on the problem, based on the situation, and we are trying to identify the appropriate test. The next one is choose level of significance. The level of significance, as we have discussed, it is alpha, that is varies from 1% to 10%, 1, 5, 10 mostly. But as far as our social science research is concerned, the widely accepted level of significance is 5%. So in general social science research, we take the level of significance as 5%. Once we fix the level of significance and selected the appropriate test, and also you have formulated the hypothesis, you are collecting the data and calculate test statistic. Collect the data. Once you collect the data from the sample, then you are calculating the test statistic. This test statistic can be t value, t calculated, z calculated, f calculated, chi-square calculated. In each test has got its own formula. Once we have the test statistic, there are two ways of making the decision. One is determine the probability associated with the test statistic. Say for example, once I got the test statistic, then I will go back to the table, then identify for this given test statistic what is the probability value. That popularly we know it is a p value. Once we have a p value, then comparing that with level of significance alpha. So your alpha is 5% and your probability p can be less than 5% or more than 5%. Based on that, we are going to reject or do not reject the hypothesis. So we are using the words two here, one is reject and do not reject. We are not using accept deliberately because there is a technical difference between do not rejecting and accepting. However, do not rejecting is deemed to be accepted. This is one way of testing the hypothesis. The second way of testing the hypothesis is, once we have the test statistic, then for a given test statistic, for a t value, the given alpha, then you are trying to identify the table value, because there are some statistical tables available, Z table, that is normal distribution table, T table, F table, chi-square table, and so on so forth. So based on the table, given the alpha value, we are trying to identify the table value. That is what we are calling as a critical value. Comparing that critical value with the calculated value, based on that we are trying to identify whether my hypothesis is rejected or not rejected. So by using these two kinds of methods, I am rejecting or not rejecting the hypothesis. Then based on that, I am trying to draw the research conclusion. The research conclusion is there is a difference or there is no difference. There is an effect, there is no effect. There is an impact, there is no impact. So that means, we are trying to understand the relationship or association and differences. Association, relationship and differences. So while we are doing the testing of hypothesis, there are two possible outcomes in hypothesis testing. They are called type 1 error and type 2 error. So let us try to understand what are these two kinds of errors. See, there is a null hypothesis, there is an alternate hypothesis, but most of the time our decision is made based on null hypothesis. If null hypothesis is true, we are supposed to accept. That means you do not reject the null hypothesis. So that is the correct decision. If null hypothesis is false, you are supposed to reject. Say for example, when you are calling some candidates for a post, you conduct the interview. If the candidate is good, you select the person, there is no problem. The candidate is not good, you are rejecting the candidate, that is also right decision. But there are also two other possible decisions we make. One decision is, when the candidate is good, we reject, or when the candidate is not good, we are not rejecting. So these two, if you understand this and you try to relate to type 1 and type 2 error, you can understand better. That means, as I told you, the candidate is good but rejected. That's where we can understand the type 1 error is when the null hypothesis is true but you are rejecting. That is type 1 error. As I said, the second one is when the candidate is not good but you are not rejecting. That is what we can understand as the type 2 error, where null hypothesis is false but you are not rejecting. That means you are accepting. So these are the type 1 and the type 2 errors, and most of the time we are trying to commit these type 1 and type 2 errors. But as a researcher, we need to have idea about these two kinds of errors, and our job is to minimize these kind of errors so that we are trying to make a better decision. Then in testing of hypothesis, we also have a one-tail test and two-tail test. So earlier while I was discussing about confidence interval, we said about alpha by 2. So if you look at this picture, there are three diagrams. One diagram has two sides blue color, and one diagram has a right side blue shade, and another diagram has a left side blue shade. So when we have two sides blue shade, the shaded part, that is called a two-tail test. When we have only one side, the shaded part, it is a one-tail test. So if it is the shaded part is the left side, it is called a left tail test. The shaded part is right side, it is known as right tail test. Say for example, the population mean is 12 and somebody is contesting that the population mean is not equal to 12. So when I am using the word not equal to, that is inequality. That inequality, when I say it is not equal to, then it is a two-tail test. Because when I am saying the mean is not equal to 12, then it could be less than 12, it could be more than 12. Whereas in the second example, what we see here, the null hypothesis says it is less than or equal to 12, the alternate hypothesis says more than 12. Then here the rejection is only one side. If it is more than 12, it is rejected. Then the next case is when the null hypothesis says population mean is more than or equal to 12, the alternate hypothesis is less than 12. So since it is a less than, it is rejection is left side, left tail test. So we can understand this through a kind of an example. For example, there is a disease for which you are taking the medicine. If you take lower dose of the drug, that may not be effective. If you take higher dose of the drug, it may be harmful to the body. That means you are rejecting the dosage of the drug. If it is too small, you are rejecting. If it is too high, you are rejecting. The second example, if you take that the right tail test, take a lift example. The lift has, for example, a maximum weight of 6 for 10 people. If more than 680 people, lift will stop and say it's overload. But anything less than 680, it will accept. In the similar way, when you go and try to buy some vegetables, then if you wanted to buy 1 kg vegetable, if it is less than 1 kg, then you try to reject that, I don't want to accept it, but it's more than 1 kg, but as long as that fellow is charging only 1 kg and it is 50 grams, 100 grams to 150 grams more also, we don't mind accepting it. So the rejection in this case is only if it is less. So that is where if it is less you are rejecting, if it is more you are rejecting, or sometimes you are rejecting both sides. So rejection is both sides is two-tail test, rejection right side is right tail test, left side is left tail test. To operationalize this, if it is the inequality, you can say two-tail test, is greater than it is right tail test, is less than it is one-tail test. The next important word which we use in inferential statistics is degrees of freedom. The number of independent pieces of information that go into the estimate of a parameter is called the degrees of freedom. So that means here we are trying to estimate the population parameter. To estimate the population parameter, how many pieces of independent information we require to estimate, that is what is called the degrees of freedom. In general, the degrees of freedom of an estimate is equal to the number of independent scores that go into the estimate minus the number of parameters estimated as intermediate steps in the estimation of a parameter itself. Say for example, you are trying to estimate the population parameter for which we may have lot of independent scores, but that scores minus the number of parameters estimated as intermediate step in the estimation, that we have to subtract. For example, the variance sigma square is to be estimated from a random sample of n independent scores. Then the degrees of freedom is equal to the number of independent scores n minus the number of parameters estimated as intermediate steps, that is x bar. Say for example, mu is estimated by x bar. When for example, when we wanted to calculate the standard deviation, we need to calculate the mean. So that means though there are n items, but to calculate or to estimate the standard deviation, I need to calculate the mean. So we are subtracting 1 from n, that is where it is n minus 1. So for operational purpose, you can remember the degrees of freedom is n minus 1. If there are two samples n1 comma n2, the combined degrees of freedom is n1 plus n2 minus 1. Then in the process we have various kinds of hypothesis tests. Say for earlier example what I have quoted is there are two populations, one male population and a female population, and I would like to look at who are the quick learners. Or there are two cities, city 1, city 2. There are two countries, country 1, country 2. Two organizations, organization 1, organization 2. I would like to look at whether those two population means are same or not, for which I can use hypothesis testing. The next one is there is something called paired t-test. Here the data is given into two components. One is before treatment, second one is after treatment. The before treatment, after treatment, before intervention, after intervention. Then I have two columns of the data. The null hypothesis says there is no difference between two columns. The alternate hypothesis says there is a difference between two columns. The test what we use here is paired t-test. Whereas in the two population means also there also we use t-test, and here we use paired t-test. It is on the same sample we are collecting the data at two intervals. One is before intervention, second one is after intervention. Then the most popular hypothesis test is ANOVA, analysis of variance. When it is a one sample or two samples, we are using t-test or z-test, and more than two samples we are going for ANOVA. This analysis of variance is a collection of statistical models and their associated estimation procedures such as variation among and between groups, used to analyze the differences among group means in a sample. It was developed by a statistician and evolutionary biologist Ronald Fisher. So in t-test we have two samples, but there are more than two samples I would like to study, then I may have to go for ANOVA. The typical t-test, the null hypothesis says regarding two populations, there is no difference between two populations as far as mean is concerned, and the alternate hypothesis says there is a difference or one is better than other. But whereas in ANOVA, when we have more than two populations, we go for ANOVA. There the null hypothesis says all means are equal, the alternate hypothesis says at least one population mean is different from others, for which we are trying to use the variance. By using the variance, I am trying to study the difference of means, we are analyzing the variance. So that is where it is the ANOVA, the full form itself is analysis of variance. It provides a statistical test of whether the population means of several groups are equal and therefore generalizes t-test to more than two groups. ANOVA is useful for comparing three or more group means for statistical significance. Again in ANOVA, we are looking at one variable, it is one way ANOVA, two variables is two way ANOVA. It is a typical ANOVA output table. So if you look at the first column, source of variation, sum of squares, degrees of freedom, mean square, f value and p value. P value or sometimes it could be f table value or f critical value. So then we are between the rows and between the columns or between the samples, and here because it is one way ANOVA, it is between the rows and between the groups and within the groups, and total sum of the total sum of the squares. And if there are total items are n minus 1, there are three groups t minus 1, then sum of the squares we have, then the mean squares are calculated, MSTR is equal to SSTR by t minus 1, MSE is equal to SSE by n minus t, then f value is the ratio between the first row mean square by second row mean square, and based on the degrees of freedom and level of significance, I can calculate the f critical value, or given f value I am converting into p value. If it is less than 0.05, reject null hypothesis. P value is less than 0.05, reject null hypothesis. More than 0.05, then do not reject null hypothesis. In the similar way, when I am looking at two variables, here there are factor A and factor B. So this is like two variables, we have some in rows and some in columns. Then here between factor A is one, factor B is another one. We are looking at between the groups of factor A, between the groups for factor B, and we have error term, then total, then degrees of freedom. And if you look at there are A rows, A groups, A minus 1 is degrees of freedom for the first row, B groups, B minus 1 degrees of freedom, total items are n, n minus 1 is the degrees of freedom. Then the error term is nothing but the degrees of freedom is r minus 1 into c minus 1, r is number of rows, c number of columns. Accordingly, sum of the squares are calculated, mean square is calculated, then f values are calculated. The advantage of two-way ANOVA is in one go we are trying to test two hypotheses related to two one-way ANOVAs. The next one is chi-square test, is a very popular test, non-parametric test, which is mostly used for cross-tabulated data in social science research. In the social science research, most of the time we have cross tabulations. Once we have cross tabulation data, we are trying to use the chi-square test. It is any statistical hypothesis test where the sampling distribution of the test statistic is a chi-square distribution when the null hypothesis is true. The chi-square test is used to determine whether there is a significant difference between the expected frequencies and observed frequencies in one or more categories. This is also mostly used hypothesis test. When we have some observed phenomena and we also have some expected phenomena, then I would like to look at whether this expected phenomena and observed phenomena both are same or different. Then also we have some more non-parametric tests. As I told you, it does not assume anything about the underlying distribution. The non-parametric tests are used when your data is not normal. The most popular non-parametric tests are sign test, two sample and k sample median test, Wilcoxon matched pairs test, rank sum test, one sample run test, and also Kolmogorov-Smirnov test. We have Wilcoxon matched pair test, then Mann-Whitney U test, then test of randomness. Like that we have so many non-parametric tests. We try to just give you some kind of a overview of inferential statistics and its relevance, and with this introduction I hope all of you had some learning experience, good learning experience, and some inputs on inferential statistics. As you know, the inferential statistics itself is a vast topic, but I made an attempt to introduce some technical terms, and with this and further reading, you would be able to conduct the test and try to draw meaningful conclusions. Thank you very much.